Hello everyone, my name is Tousif Ahmed and I would like to present our work on remote breathing rate tracking using the motion and acoustic sensors of the Earables. I am presenting this work on behalf of our research group in the Digital Health Lab at Samsung Research America, where we work on developing novel technologies for remote health monitoring. This work mainly presents our effort on breathing rate monitoring. So breathing rate is a critical vital sign, and daily monitoring of breathing rate has significant health and wellness benefit. A healthy adult takes 12 to 20 breaths per minute, and abnormalities in resting breathing rate often associated with severe medical conditions like cardiac arrest, pneumonia, and respiratory infections. Breathing rate is a highly desirable feature for those who have respiratory diseases because it could lead to early identification of condition exacerbations. However, it is very difficult to monitor the breathing rate outside hospital. People can track their breathing rate either by manually counting the number of breaths per minute or using an expensive device like a respiratory belt or chest band. Manual counting is not very accurate and chest bands are not very accessible options. So recently there have been some effort on using mobile and wearable devices for breathing rate monitoring. So breathing produces a subtle body movement and sound that can be recorded by motion and acoustic sensors. So when we breathe, we have a periodic movement, and if we check the recorded or motion sensor, we can see the same periodic pattern here. And when we breathe, it generates a very distinct audio signature that can be visible on the frequency domain here. So previous works showed that it is feasible to use motion and acoustic sensors and calculate the breathing rate very accurately. However, most previous works only use one type of sensors. Breathing produces a very small body motion and sound, so any non-breathing movements or background noises can easily mask these types of recordings. For example, here as you can see that breathing sound is captured perfectly, but motion sensor is masked by a sudden heavy body movement. On another occasion, motion sensor recording seems to be perfect, but breathing audio is masked by the background noise. When it happens, it is very hard to recover the original signal from these noisy signals. So the best approach we can do here is to discard the noisy signals. However, if we use single modality, we will be dropping too many recordings that might impact the usability of the system. For example, just think that the user is probably actively trying to know their breathing rate, and slight movements or background noises discarded the recording, so they are not able to do it, or they are not getting their breathing rate for those occasions. So this might demotivate the user for using the system. So we argue that a single modality will not be enough for breathing rate monitoring with good utility. We need a multimodal solution. However, one challenge is most devices are not suitable for multimodal recordings. Phone can use multimodal, but it needs very inconvenient settings, which is not ideal. Watch are located really far away and it cannot record the breathing sounds. Fortunately, the new generation Earables seems to be very convenient and very well suited for capturing breathing related motions and sounds. However, a multimodal approach is not explored yet using the Earables. So to address the gap in the literature, we propose a very simple and lightweight multimodal solution for breathing rate monitoring. So we use a motion sensor first solution where we use a signal processing based approach to estimate the breathing rate using the motion sensors. If the motion sensor is failed to determine the breathing rate, then we run a little bit heavier audio-based pipeline that utilizes machine learning to estimate the breathing rate. Finally, we show it to user application. Here we prioritize the motion sensor to keep the system lightweight. And this approach is totally implementable on the low resource earbuds, which reduces the data transfer overhead for the system. Now, I'm going to briefly discuss the pipelines. So we first determine the head motion from the sliding window in the motion sensor based pipeline. If the signal has low movement, then we perform a list of signal processing steps to calculate the breathing rate. Simply, we take some of the recorded axes and take one of the most periodic axes from there and filter the raw signal using a series of noise filtering steps to obtain the clean periodic signal as this one. Once we have clean signal, we determine the number of cycles detected using the 3 well-known algorithms and calculate the breathing rate at the end. We can also determine the quality by taking the standard deviation of these 3 breathing rate estimation and perform some post-processing to generate the final breathing rate from the motion-based pipeline. So for the audio pipeline, we use a machine learning based approach where we extract features on small windows and run a lightweight machine learning classifier to detect the transition points. Here, transition point means the start of the breathing phases, like the start of the inhalation or exhalation phases. So the machine learning classifier is trained in such a way so that they can determine the periodic transitions and it can distinguish it from the non-periodic noises. So once we detect the transitions, then the duration of these transition points is used to determine the final breathing rate. So to evaluate and develop our approach, we conducted one of the most comprehensive data collection study in this research area. We collected data from 30 participants for 7 days in both lab and home environment. Our participants performed both breathing and non-breathing tasks in 3 postures during the participation in the study. We collected the ground truth breathing rate using an FDA approved respiratory belt. And at the end of the study, we collected more than 2,500 breathing sessions in both lab and home environment. The participants were very compliant and almost all participants contributed more than 25 sessions. And in some cases, participants contributed more than 70 sessions. So when we ran our approach on the collected data, we used 2 metrics to evaluate the performance. One is mean absolute error, that is the absolute difference between the ground truth breathing rate and prediction, and the retention rate, that is the percentage of session that the system was able to retain. And what we found is that the multimodal option actually retains most amount of data, while the motion-based approach sometimes fails due to the heavy noises. For example, during standing, the users are like moving more frequently, so the performance was not good, but audio complemented that, and that improves the performance of the multimodal case. So in multimodal case, we are able to retain more data with a good accuracy. Another key result is that we can control the accuracy and retention rate by our filtering technique. So if we use very aggressive filtering, we can improve the accuracy, but it reduces the session retention, while minimal filtering improves the retention, but at the cost of the accuracy. And we selected a moderate filtering so that it gives us the best of the both worlds. As our goal was to develop a very lightweight system, we identified that we can implement both motion sensing and audio-based pipeline on the device itself, and it takes very minimal resources. The motion-based pipeline takes almost negligible amount of battery and memory, while audio-based takes a little bit more than that. However, the audio-based pipeline is not activated most of the time. It mainly focuses on the motion-based pipeline. This kind of indicates that like our system is capable of running continuously without taking too many resources. So the key takeaway from this work is that we present a multimodal approach for breathing rate monitoring using earbuds that can accurately calculate the breathing rate while retaining most of the breathing sessions performed in the real world settings. These results can inform the designers to design a better interaction technique for a quick breathing rate measurements for the users. For example, they can use these results to identify suitable positions, and they can also instruct the user to go to a suitable position so that like we can estimate the breathing rate pretty accurately. Finally, our lightweight system can be extended to a passive monitoring system where it might not require any user interaction from the user. So this might give us the first passive breathing rate monitoring solution in the future. So that's all from me today. Feel free to reach out to me with any questions.